Welcome. And we are moving on into chapter 7, which deals with periodic trends in the elements. And so we're going to focus really on four things in chapter 7. There's some stuff toward the end about various groups of the periodic table that we're not really going to focus on, but these are the four things we're going to talk about. Sizes of atoms and ions, so that's called atomic radius or ionic radius. Ionization energy, and I'll describe in just a few minutes what that is. Electron affinity, that won't be in this video, and then electronegativity, which is in chapter 8 in your textbook, but I'm going to move it into this conversation in chapter 7 because it's related to, the trends are related to these other things. So this video is actually going to focus on size of atoms and ionization energy, but before we do that, we're going to talk about something called effective nuclear charge. And that's because there are some very strange things that may seem counterintuitive to you when it comes to comparing the properties of some elements. And so I'm just going to start by asking you a question up front before we've learned anything in this video, which is think about lithium, which is element 6, and neon, which is element 10. They're both in period 2. Lithium, being element 3, has 3 protons and 3 electrons. A typical lithium, most common isotope of lithium is 7, and so it would have 4 neutrons. So it would have a mass of 7 atomic mass units. Neon, being element 10, has 10 protons and 10 electrons. The most common isotope of neon has 20. It has a mass of 20, so it's got 10 neutrons. So if I asked you to tell me which of these two atoms is larger and by how much, lithium, which is element number 3 with a mass of 7 atomic mass units, or neon, which is element 10, the mass of 20 atomic mass units, it must necessarily be lithium, right? Well, lithium has a diameter of 2.68 angstroms. Remember, an angstrom is 10 to the minus 10th meters. Neon has a diameter of just almost exactly half the diameter of a lithium atom. Now, how is that even possible, that a thing that weighs like 3 times as much has more than 3 times as many particles in it, actually is smaller in diameter, only half the diameter? Well, to answer that, we're going to talk about a property known as effective nuclear charge. But before we do that, I even want to circle back onto Coulomb's law. It's important to remember Coulomb's law, and the College Board is always eager for you to do so. And if you'll recall, we talked about this earlier in the year. Coulomb's law says that the force between 2 charged particles is equal to the product of their charges divided by the square of the distance between them. So R is the distance between the 2 charges. In the case of atoms, it would be the distance between the nuclei. And energy, the energy of the system, is equal to the product of the two nuclear charges divided by the radius. That is the R, which is the distance between the 2 nuclei. And so just kind of think through what the implications of that are. Force and energy are directly proportional to the magnitude of the charge. Therefore, if Q1 and Q2 get bigger, the force and the energy, the force between them and the energy of the system is going to go up. These things are inversely proportional to distance. So as R gets larger, F and E actually get smaller. And then the last thing to remember is that like charges repel each other and opposite charges attract. So you would have a positive force if, say, these were both positively charged, they'd be being pushed away from each other. That'd be a positive force. If they were oppositely charged, they would be being pulled toward each other. That would be a negative charge. If you had, in terms of energy, if you had like charges, the closer you get them together, the greater the energy of the system. If you got opposite charges, the closer you get them together, the lower the energy of the system. So let's talk about effective nuclear charge because it underlies everything when it comes to atomic radius, ionization energy, electron affinity, and electronegativity. So, and the ionic radius is really going to be determined by how far the valence electrons, that is the outer shell electrons, are from the nucleus. And remember, valence shell electrons are negatively charged, so they're going to be attracted by the positive charge of the nucleus. But valence electrons in a many electron atom, which is pretty much everything except hydrogen, don't really experience the full nuclear charge. And we'll talk about what we mean by that in just a second. In the many electron atom, the electrons are both attracted to the nucleus, but they are also repelling each other. And that has the effect of what's called shielding. And so the nuclear charge that an electron experiences, whether it's a valence electron or a core electron, is going to depend on the nuclear charge as well as how many other electrons are between it and the nucleus. And so you have this concept of screening, and valence electrons tend to be screened from the nucleus by other electrons, and that is particularly true that they are screened by core electrons. And so if we think about a sodium atom, which has 11 electrons total, 10 of which are core electrons, and the 11th is the 3s valence electron of a sodium atom. Those core electrons are going to tend to screen this electron from feeling or experiencing the entire charge of the nucleus. And therefore, it won't be pulled in as far as it would be if it did experience the full charge of the nucleus. So we can calculate what's called the effective nuclear charge. And the effective nuclear charge is simply the nuclear charge that valence electron is actually experiencing. It's equal to the actual nuclear charge minus the screening constant. And the screening constant tends to be fairly close to the number of core electrons. And so for example, a sodium atom has 11 electrons, 10 of which are core. The nucleus has a charge of 11. And so the effective nuclear charge for a sodium atom for the valence electron is about 1, positive 1, because the Z effective is going to be equal to the Z, which is 11, and the screening constant is roughly equal to the number of core electrons, which is 10. So 11 minus 10 is going to give you a 1. Here's a diagram from your textbook in which this green line, this green curve, represents using that exact rule, and that is that core electrons will screen a valence electron by exactly 1 proton per electron. And what you get is that then everything in group 1, whether it's lithium or sodium, experiences an effective nuclear charge of 1. Everything in group 2, whether it's beryllium or magnesium, experiences an effective nuclear charge of 2, etc. The truth is that the reality is a little more nuanced, but you can see that it's certainly true as you go across a period, effective nuclear charge increases, and that is because core electrons are better at screening valence electrons from the nucleus than fellow valence electrons are. And so if we look at, and so what I've done is I've just taken this graph down here, the blue graph, which shows the actual reality using advanced methods of calculation for what the effective nuclear charge is. And I put that into a table here. So these are all the elements in period 2, beginning with lithium and going all the way through neon. And you'll see that lithium experiences an effective nuclear charge of 1.2, which is close to 1, which is what we said things in group 2 were, in group 1 were likely to experience. Neon experiences an effective nuclear charge of about 6. And so that's about 5 times as much. It is feeling a positive charge from the nucleus, which is about 5 times as much as what lithium is feeling. And therefore, if you then add onto the table what the actual radius, atomic radius of all of these items, earlier I gave you the diameter, but usually these things are actually given in a tabular form as radii. But the atomic radius of lithium is 1.34, and then it goes down to beryllium, down to boron, it's just going down, 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 because those outer electrons are feeling an increasingly larger nuclear charge. And remember, opposite charges attract, according to Coulomb's law, and so that's going to tend to pull those valence electrons in closer to the nucleus and make the total size of the atom smaller. But even though these atoms are getting heavier, they are actually also getting smaller in the same group because because they're experiencing a larger effective nuclear charge. How do we measure the size of an atom? There's really a couple different ways to talk about of radius. One radius is from the nucleus to the outer edge of the electron cloud. We'd call that the non-bonding atomic radius. And then we can also talk about the bonding atomic radius, which is simply 1/2 of the distance between two nuclei in a bond between two atoms of the same element. And we talked earlier in the year about there's an ideal distance for these things to get apart, in which the attraction between the nucleus of one atom and the electrons of the other, they want to get closer together for that reason, but they reach a maximum point at which now there's too much repulsion between the two nuclei. And so there is an ideal length. And so when we're talking about bonding nucleus, a bonding radius, we're simply talking about half the distance between these two nuclei. And so here's the table from your book. It's kind of a heat map kind of table showing what the atomic radii of all the elements are, at least all the elements in the first 5 periods. The bonding atomic radius tends to decrease as you go from left to right across a group, across a period, because of the increase in effective nuclear charge. And it tends to increase as you go down a group, and that's because you're adding shells, right? You're adding principal energy levels. And so even though there's not a big difference in the effective nuclear charge experienced by a lithium and a sodium, because the sodium valence electrons are in a higher energy level, they're going to be further from the nucleus. So as you go down that group, the atoms get larger. And so I've taken that and I've tabulated it in a view that's a little bit easier to see. But you can see, as we were showing before, from lithium through neon, it just keeps going down with every one. And if you do the same thing, sodium through argon, as you go from sodium to magnesium to aluminum to silicon, et cetera, the atomic radius just keeps going down. Again, this is counterintuitive to what you might think. The bigger, the heavier, higher order element you would expect to be larger, but as long as they're in the same period, they actually get smaller as they go up. Going down the same group, you'll see that they get larger, 0.32, 0.69, 0.97. All these things in period 3 are larger than the thing above them in the same group in period 2. And in period 1, you can see again that they're getting larger. Okay, that's the radii of atoms. We can also talk about the radius of an ion. And so the common ions of all the main group elements are shown here. And you can see something that actually makes a lot of sense, and that is when metals lose electrons to form cations, that makes them smaller. And it makes them smaller really for 2 reasons. A, you are taking away electrons, and that decreases electron-electron repulsions and makes it easier for them to feel a higher effective nuclear charge. But also in these cations, you are also stripping off all the electrons from the valence level to get down to have the same electron configuration as the previous noble gas. And so you're taking off the entire valence level of electrons, which is going to also make that smaller. By contrast, when you add electrons to an element to make it an anion, what you see is that that anion is larger than the parent element, and that's because you are adding electrons. The nucleus is less effective at pulling them in, and they're repelling each other more. And so this is just explaining that when you make a cation, they're smaller because you're taking out the outermost electrons. So you're removing an energy level, and repulsions are less. When you make anions, you are increasing repulsions between electrons, and that's going to decrease effective nuclear charge and make them larger. So as you go down a column, just like with the size of an element, size of the native atoms themselves, you are going to get larger because you are adding principal energy levels. And it's the same thing as you go down a group of anions, again, you are adding on principal energy levels, and so they get larger. The last thing to talk about is what's called an isoelectronic series. And an isoelectronic series is a series of ions that all have the same number of electrons. And so I've highlighted an isoelectronic series here. The oxide ion, the fluoride ion, the sodium cation, the magnesium cation, and the aluminum cation all have 10 electrons. Remember, when you ionize, you're trying to be like the nearest noble gas, and the nearest noble gas to all of these things, oxygen, fluorine, sodium, magnesium, and aluminum, is neon. And therefore, oxygen gains 2 to be like neon, fluorine gains 1, sodium loses 1, magnesium loses 2, and aluminum loses 3. Also, they can be like neon. And so they all have the same number of electrons, but what you can see is that as you go along the isoelectronic series, their radius is getting smaller. And that should make sense to you because they have the exact same number of electrons. But as you go from left to right and then down and continue to go through this, there are more protons in the nucleus, greater effective nuclear charge, smaller ionic radius. So that is atomic and ionic radius. Let's now get to the last bit, which is what's called ionization energy. And we define ionization energy as the amount of energy required to remove actually a mole of electrons in the ground state from a mole of gaseous atoms or ions. And so this is always given as kilojoules per mole. So the first ionization energy is the energy that's required to remove the first electron from a mole of atoms. The second ionization energy is going to be required, is the energy required to remove a second electron from a particular thing, a mole of second electron. And so if, for example, we were talking about magnesium, which has 2 valence electrons, the first ionization energy would be the energy required to remove a mole of electrons from magnesium so that you had magnesium plus 1 cations. And then the second ionization energy would be the energy required to remove a second mole of electrons from the magnesium so that you now had magnesium plus 2 cations. Well, I've listed the trends in first ionization energy here. I've given the first ionization energies for the first 18 elements of the periodic table. And this is all based on effective nuclear charge. As you go from left to right across a period, effective nuclear charge increases, and therefore the ionization energy increases because those electrons are closer to the nucleus. They're therefore more difficult to strip off. They're being more tightly held. Same thing as you go across period 2. It goes from lithium has a small effective nuclear charge, therefore a small ionization energy because it's a large atom. As you get over to neon, which has a large effective nuclear charge, got a very small radius compared to lithium, it becomes much, much more difficult to remove a neon electron because those neon electrons are being held closer. Again, Coulomb's law is coming into play here. Same thing as we go across period 3. What you'll also notice is that consistent with effective nuclear charge and with atomic radius, as you go down a group, the ionization energies go down because these electrons are further from the nucleus. Argon's electrons are further from the nucleus than helium's, and therefore the electrostatic attraction between those valence electrons and the nucleus is not as strong. Therefore, they're easier to remove. Now, there are a couple little glitches in this. And so, well, let me just say, as you go across a row, it gets harder to remove an electron. But there is a discontinuity here between groups 2 and group 3. You notice actually it goes up for beryllium, which you would expect, but then it drops back down for boron before it starts going back up again. Why would that happen? Well, that has to do with some things we learned back in chapter 6 about orbital electron configuration. You notice that beryllium, and it would be the same thing for magnesium, has exactly a filled 2s subshell, whereas boron, and it would be the same thing for aluminum at the 3 level, now has a p electron. And so it turns out that it's easier to strip off that 2p electron than it is to try and pull an electron out of this completely filled 2s subshell. And so that's why actually beryllium is a little bit higher than boron. And the same thing, magnesium is a little bit higher than aluminum. Then the other discontinuity is between groups 5 and 6. You'll see again, once we get through that first discontinuity, it starts trending back up again, but then it drops down a little between nitrogen and oxygen, and it does the same thing between phosphorus and sulfur. Well, that also has to do with electron configurations. There's also particular stability in an exactly half-filled subshell. You'll notice that nitrogen has a filled 2s subshell, and it has exactly a half-filled 2p. That actually imparts a certain amount of extra stability, and so it's harder to take an electron out of there. The electron you're taking from oxygen is actually a paired electron, and it is a little more willing to go than one of these electrons, because these will disrupt the special stability of an exactly half-filled shell. Okay, the last thing to say about ionization energies is to say that as you start stripping more electrons off, it gets harder to do. If you look at aluminum, the first ionization energy is 578, second is 1817. It keeps going up, going up, going up. Then what I want you to notice is this stair step here where it really makes a huge leap. And the reason that's the case is because now when you're getting over into the shaded area on the right-hand side of the stair step, you are removing core electrons, right? So sodium has one valence electron. It's pretty easy to take off. When you then try and take a second electron from sodium, now you're taking a core electron, and that's really, really hard. So you'll notice every time the stair step, it jumps by a factor of like 3 or 4. And that's because you're going from trying to remove a valence electron to trying to remove a core electron. Okay, well, that's all that I have for this video. So thank you for watching. Check out the suggested practice problems, and we will see you in class. Thanks.